Okay, oops. There we are. So that's the quiz on Wednesday. After this lecture, I am going to be posting all of the lecture notes for continuity all together, like I did for compactness. Okay, so you'll have all of that. Please interrupt me if you have any questions, as usual. Today, we are looking at continuity and connectedness. This is section 2.4 of Tau, and I know we've been deviating from Tau quite a bit, so I will just mention that in this instance, we are actually going to follow Tau really closely. Okay, so I'll still be posting lecture notes, but his book and our lecture notes are going to agree on everything today. Okay. Using compactness, we gave this generalization of the extreme value theorem. Okay, you remember we proved if you have a compact domain and a continuous function, then your range is also compact. So if your continuous function is mapping into the reals, your range is going to be closed and bounded. And so you're going to actually achieve your min and your max. Okay, so that was our big generalization of the extreme value theorem. If you remember back to last semester, another big theorem from calculus is the intermediate value theorem. Remember, the intermediate value theorem says if you take on, if a continuous function takes on two different values, then it takes on all the values in between. Okay? Our generalization of that involves connectedness. Okay? So we're going to start with just like what is connectedness for metric spaces, and then we're going to prove that it's preserved by continuous functions, and then we're going to show. I'll leave some mystery here. We're going to characterize the connected sets on the real line, and then we're going to get the intermediate value theorem as an immediate consequence. Okay? Okay, so what does it mean? We're going to have three definitions here. The first one is, what does it mean for a metric space to be connected? Okay. Well, imagine you could draw your metric space. Your metric space is this thing. Is that connected? What should connected mean? There are several possible definitions of connected. The one that might come to mind, or the one that you might think of as natural, is kind of, if you take any 2 points, you can get from one of them to the other by staying inside the set. Okay. Now technically, we call that definition path connected. Okay, you're path connected if you can get from one point to any other by staying inside the set. And you have to make some rules, what's your path allowed to do? Does it have to be continuous? All these things. You have to make some rules there. So that definition actually gets a little bit complicated. And so we're going to use the easier definition, but it's a little bit less intuitive. Okay. So here is our definition. We're going to start with what it means for metric spaces. Then we're going to say what it means for a set in a metric space. So this is the definition of connected metric spaces. And we define it by its negation. So we're going to say what it means for a metric space to be disconnected. So the metric space XD is disconnected if our example was clearly connected. Let's do I guess we should motivate this with a disconnected set. What would a disconnected metric space look like? Well, one thing you might say is disconnected is if you just have those two blobs and you can't get from one to the other. Okay. So you're disconnected if and only if there exist few conditions here. Put them in green to set them apart. Disjoint, non-empty, open sets. U and V such that X is the union of U and V. Okay, and according to this definition, we define connected as the opposite. Okay. So our example where I said it's clearly a disconnected metric space. Well, both of each of those two blobs is an open set. Or at least it should be an open set, because for every point there's a neighborhood in that. You know, even if we take something on the boundary of this blob, I'm taking this red point on the boundary of this blob, we consider a neighborhood of it. Okay, so we draw a little ball. But the blue stuff's the entire metric space. So actually that neighborhood doesn't contain this, this stuff outside. So the neighborhood's in the set. So the way you should think about these disjoint, non-empty open sets is we could draw an open set containing one of the blobs and an open set containing the other blob, and they wouldn't have to intersect. These are open sets. Okay. And again, our definition is only for metric spaces, but we'll make it for sets in kind of the obvious way here in a minute.
I'm a bit confused about the drawing. So here, the open sets are the things in green, and like the U and V are the things in green, but the stuff in blue is the metric space?
Yeah, so, right. So there's nothing that's in green but not in blue.
Okay, all right.
The green, the fact that I drew the green as bigger just kind of is supposed to indicate to you that, yeah, we could make a technically open set that contained that blob.
Okay, thanks.
What happens if the metric space is closed and we have these two closed blobs?
Well, remember, all metric spaces are closed.
Oh, right.
The set X is always closed, and the set X is always open.
Oh, so, okay. There goes me using English, thinking the opposites.
So when you consider a neighborhood, when you consider a ball, because say you're trying to satisfy the definition of open, you only consider the points that lie in the metric space. So like in this example, you're it might look like the ball lies outside the metric space, but obviously nothing lies outside the metric space. I hope this will be cleared up once we get to our definition where we're going to define connected sets within a metric space. Okay, but before that, I want to do an example of this definition. So if you're not happy with this definition, just for right now, take it as the abstract definition. We're going to play with what it says, and then we're going to maybe have a slightly more applicable definition here in a minute. So here's our example. Consider a discrete metric space. What are the open sets in the discrete metric space?
Every set is an open set, and therefore every set, and therefore like the metric space will always be disconnected.
Very close. It's not quite always disconnected. What's the exception?
Oh, when there is only one point.
Yeah, or zero. Or
Oh,
zero.
Yeah.
Okay, so if x has at least 2 points, then it's disconnected. Because we can take one of our open sets to be just a single point, and the other open set to be the complement. Okay. And then we just check the conditions. Are they disjoint? Yeah, one is the complement of the other. Are they non-empty? U is certainly non-empty, and we assume that x has at least 2 points, so V is going to be non-empty too. And are they open? Yeah, with the discrete metric, every set is open. Okay. Questions about that example? I hope this is one point of evidence in favor of our definition being a good one, because I think it's natural to say that discrete metric spaces should be disconnected. Right? You can't really move from one point to another in a discrete metric space. Oh, good question in the chat by Abby. Why are we only, why in the definition do we only allow 2 sets, U and V? Why not say you're disconnected if we can break you into any finite number of open disjoint, non-empty sets? The answer is that we could do that. Yeah, Daniel has a hint to the answer in the chat. We could do that, but we wouldn't gain anything. So if X is, say, U1 union U2 union UN, then we could just do this. Okay, we could take the union we could take the first one, and then the union of all the others. And if we had the conditions on U1 through UN, then we'll still have the conditions on these two open sets. They will still be disjoint, non-empty, and open. Okay? So if we expanded the definition of disconnected to let ourselves break into multiple parts, it wouldn't get us anywhere. Okay, so we just stick with the definition where we break it into two. Does that make sense? Okay. Now, I want to focus on this discrete metric space example we just did. What did we do? Here, we let V be the complement of U. Now you think about it, go back up to the definition of disconnected. We're insisting our sets be disjoint, and we're insisting that together they contain everything in X. Okay? That means V always has to be the complement of U. Okay? Or if you want to put it in another way, our two sets U and V have to be complements of each other. Okay? So so if we're disconnected, if our space X is disconnected, then our set V has to be X minus U. Okay, what does that mean about the set U?
It means that it is closed and open at the same time.
Mm-hmm. Yeah. So U is closed because V is open, but we already said U was open. So U is both. And we'll use this term clopen for that. Okay. Now, you can actually go the other way. If you have any non-trivial, well, okay, so let me say this. In any metric space, the empty set is clopen and the whole set is clopen. They're both closed and open. If you have any other set that is both closed and open, anything other than the empty set of the whole space, you can do this same trick, and you can say that your space is disconnected. Yeah, V is also clopen. V is also clopen, as Benjamin points out in the chat. So if we do have a clopen set, and it's not one of the trivially clopen sets, then our space is disconnected. Okay. So what have we proved? We've just proved that it actually goes both ways. If you're disconnected, you have a non-trivial clopen set. And if you have a non-trivial clopen set, you're disconnected. Let's just write that down as a proposition. And because the first one was phrased negatively, let's phrase this positively. So this metric space is connected if and only if the only clopin sets, subsets in there are the empty set and the set itself. Okay, any questions about that result?
This is maybe a thought towards the future. So we want to show that if the space is connected, we want to show that there are none of these clopin sets. So we're going to like try to say, you know, suppose a set is open, we show that it can't be closed, or vice versa. Is that a strategy that we're going to use?
No, no. I mean, it's a valid strategy. But we're really only going to prove, today at least, we're only going to prove that one particular type of set is connected. And we're not going to use that strategy. Okay. But it's a good thought. Okay. So far, we have only defined connected for metric spaces. And we really want to talk about sets within metric spaces. The way we do that is sort of I would claim it's the obvious way. We're just going to restrict the metric space to the subset we care about and ask whether that induced metric space is connected or not. So let's work through this definition. We're going to start with an ambient metric space XD. Okay. Then we're going to take a set Y in there. We're going to define it to be connected. Or, for that matter, disconnected. If and only if the induced subspace oops, I realized I didn't want to it's kind of a pain. To be technically correct, okay, I want to call my metric on X just D, because now I'm about to restrict it and it would look really bad if that were a D sub X. Okay, if and only if that metric space is connected / disconnected. Good. This is our first time, I think, doing a definition this way. But we could have done the definition of compactness this way as well. Okay, so compactness we actually did exactly the opposite way. We defined it for sets, and then we extended it to talk about a compact metric space. But we could have defined a compact metric space and then said a set within a metric space is compact if, when we restrict to that set, we have a compact metric space.
Why is this phrased as a definition instead of like a proof? It seems like, can't we deduce this from our other definition?
No. This is a definition. Because it's the definition of connectedness for sets.
Okay, I see now.
Before we only defined connectedness for metric spaces, and now we've got it for sets.
Okay.
I mean, and this is saying it's the same definition.
Okay.
Okay, so now let's go back to this example up here. Our very beginning example. I said assume the blue points are the metric space. Okay? And now I can say, well, assume the blue points are your set, and your metric space is like R2 with the Euclidean metric. Okay? Then that thing being disconnected, to test whether it's connected or disconnected, we look at the metric space, the R2 with the Euclidean metric, restricted to the set of points in blue. Okay? In that restricted metric space, we find that these green, these sets with the green borders are open. Now, you think back, they're open in the restricted metric space. That means that they're relatively open with respect to the blue set. Okay, so we're getting into relatively open here. Let me just make that note here. So recall the open sets in this restricted metric space are the sets, this is the definition really, the sets that are relatively open with respect to Y in the big metric space. Okay, this goes all the way back to something we did in like the second week when we looked at relative topology. We proved that the sets that do this, so the sets that are relatively open with respect to Y are precisely those. Does anyone remember the results?
It's the intersection of an open set in the big space with the small space.
Yep. Okay. To be relatively open with respect to Y means you are an open set in the big space intersected with Y. Okay. Now, the other way to say that to be open in the small space, you have to be an open set in the big space restricted to the small space. Okay? Now, if you go back to the picture of the very first example, I guess it was the second example because we erased the very first example. Now, if you think about the blue set as being inside R2 with the Euclidean metric, then I can say that the green would actually be the open sets in the big space. They would be the open sets in R2 with the Euclidean metric. And those are the open sets that are showing us that our blue set is disconnected. Does that make sense? Let's do an example. Okay, let's stick to the real line with the standard metric just to be comfortable. And let's take our set to be the interval from 0 to 2, but we'll remove the point 1. And that set is going to be disconnected. So what do we need to do? We need to find some sets that are relatively open with respect to that set, but are also disjoint disjoint, non-empty, and open. Sorry, disjoint, non-empty, and open, relatively open with respect to that set. And together, their union has to be the whole set. Well, it has to cover the whole set. Okay. We could cover this whole set by looking at these half-open intervals. Okay. Their union would be this whole set we're talking about up here, right? If I union these two guys, I will get that set, the interval from 0 to 2, with the 1 removed. Okay, and I claim those two are both relatively open here, because the first one I can write it as the open interval from -1 to 1 intersect with my set. And the second one, we can do the same thing. We can go 1 to 3, intersect with our set. So these are both relatively open with respect to, I'll abbreviate it as WRT, this set. Okay. And you can just check, we've got the conditions. We are disjoint, non-empty, and open in the submetric space, the metric subspace, the subspace of the metric space. Any questions? Okay, that's enough on the definition of connectedness. I will grant you that it's a little bit weird, this definition. I think we'd all be happier talking about path-connected things. But again, we don't really want to get into that because then we have to set all these rules on what a path is. So this is sort of the more abstract and actually more user-friendly when you get used to it definition of connectedness. Now, it's time to actually prove something. Let's prove a theorem. Connectedness is preserved by continuous maps. Okay, it's just, we're going to have a domain and a range, domain and a codomain, sorry. We're going to have a function that goes from x to y. It's continuous. And the domain is connected. Then, what can we conclude? Any guesses?
The image of X is connected.
Yep. Notice that it's the image of X, it's not Y. Okay. I mean, that's just kind of a general principle. You can never conclude anything about the codomain. You can only conclude something about the range. Okay. Clock says we got 13 minutes. I think we can do this one. This is not a hard proof. You can kind of see what's going to happen. Connectedness is open sets. Continuity is that the inverse image of an open set is open. So we're going to suppose to the contrary that Y is disconnected, and then we're going to map those open sets back into X, and we're going to disconnect X, and that's going to be a contradiction. Okay, let's do it. So let's suppose U and V. Okay. Except arguing by contradiction would work, but this is one of those cases where you can actually avoid the contradiction. And so I think it's a little bit nicer to avoid the contradiction. So I'm going to suppose that U and V are disjoint open sets open, I think I want to say subsets of the image such that the image is U union V. Okay, now what do we want to show?
If we're able to show that the pullback of U and V, the union of those is X, then we have that X would be disconnected.
That would be true if we were arguing the contradiction, but we're not. Okay, so the question, let me ask it a little bit differently. Have I assumed that the image of X is disconnected here? No.
Almost.
Almost, but I haven't, right?
we need to show that one of those is the empty set.
Yeah.
And then the other is FX.
So if the image of X were connected, then whenever we did this, whenever we had these sets U and V, one of them would be empty. Okay? So that's what we'd actually like to show, is one of them's empty. Okay, now let's pull them back. Let's look at the preimages. These are both open. In the domain, because F is continuous. Okay. Moreover, X has to be the union of these two things. Okay, every point in the domain has to be in either A or B because it got mapped to either U or V in the image. Okay? And the intersection of A and B has to be empty. Why is that true?
A function can't map an element to two different elements.
Yep. Yep. If you had something in A intersect B, its image would have to be in both U and V, and we assumed that U and V are disjoint. Okay? Now, let's just recap here. Therefore, A and B are disjoint open sets with their union equal to X. Since we assume that X is connected, either A or B must be empty. And now we're done. Okay. If either A or B is empty, then either U or V is empty. So, you can't have disjoint, non-empty open sets in the partition, the image. Because if you had any, disjoint open sets whose union were the image, then one of them would be empty. Okay? So that's the not proof by contradiction here. Okay. We would only take, you'd only have to change a few words to make this into a proof by contradiction. But I didn't do that. Okay? Any questions on that one? Okay. In that case, we've got 5 minutes. So I think the best thing to do, we have 2 more results coming. Let's state them, and then we can go talk about the proof of one of them. I mentioned this earlier. I didn't give away the answer, if I remember right. The connected subsets of the real line with the standard metric are precisely what? What are the connected subsets of RD? Benjamin says closed and bounded intervals. Well, do they need to be bounded?
Well, I guess they don't, because you could just take the whole real line and that would
Yeah.
be, but that is closed.
Okay,
Well, it's not bounded, it's not bounded.
It's not bounded. Do they need to be closed?
Intuitively, I would say yes, because you have to worry about the endpoints. Oh, no, I guess they don't. No, I guess they don't need to be closed either. I guess they would just be intervals.
Yep. The connected subsets of the real line with the standard metric are precisely the intervals. I guess we're not going to have much time to talk about the proof of this. The proof will be in the notes. I really encourage you to take a look at it. One direction is pretty trivial. If you're not an interval, then you're not connected. Okay? Now, how do you prove that? You remember back to last semester, very early on in last semester, we proved that the intervals are precisely the sets that satisfy the betweenness property. Remember that betweenness property. Okay, so if you're not an interval, you fail the betweenness property. That means that you have some, I'll do it up here in the upper right, you have some real numbers, x, y, and z, such that x is in your set, y is in your set, but, sorry, z is in your set, but y is not in your set. Okay? Well, now what do? Y is where you can split your set into 2 parts. You now take your set, and the stuff to the left of y, and your set and the stuff to the right of y. And then what have you done? You have, because y is not in your set, if you're not an interval, you fail the betweenness property. So there is some y that does this. And now you've partitioned your set into 2 disjoint, non-empty, open sets. And therefore you have shown that your set is disconnected if it is not an interval. Okay. The harder direction is showing that if it is an interval, then it is connected. Okay. That is a proof by contradiction. Okay, the details are in the notes. I will leave that for the notes because I'm literally out of time, but if you'll permit me another minute or 2, I need to state the intermediate value theorem. Here's how we stated it last semester, basically. if your function is defined, your function's domain is an interval, and it's continuous, then its image is also an interval. Okay. That is the intermediate value theorem. That's immediate from the results we talked about today. Okay. If your domain is an interval, then by the theorem above this, it's connected. By the theorem before that, your image is connected, and because it's a connected subset of the real line, it's an interval. Okay? So there we are. That's continuity and connectedness, giving us this nice generalization of the intermediate value theorem that holds for any metric space. And actually, so now one thing, you should go back and think about some exercises you've done maybe. Here's a nice one now. Characterize the continuous functions from the real line to a discrete metric space. Right? The real line is connected. We just talked about the connected subsets of a discrete metric space at the beginning of today's class. And now this theorem we just proved, right, lets you nail those down. Okay, this is the conclusion of continuity, of our discussion of continuity. So we're done with chapter 2 of Tao's book, and we'll be done with chapter 3 of the lecture notes that I'm going to post for you later on today, and that'll be the topic for the quiz on Wednesday. And other than that, feel free to drop by to my office hours later on this afternoon at 1:30, or tomorrow morning, or Nicole's office hours tomorrow, or otherwise, I will probably see you on Friday, although I'll be here in the Zoom room for our quiz on Wednesday. So, okay, have a great rest of the day, everybody. Bye-bye.